G'day everyone, welcome to the video. Today we're going to be looking at rates of change, and we've been talking about in calculus that when we talk about dy dx, that's the rate of change of y with respect to x. In other words, how much is y changing, increasing, decreasing as x changes. So they're sort of like relative rates. How is y changing in relation to x? And that's good. Hopefully, understand that. Then we know that dy dx is the gradient because the gradient tells us how much y is changing with respect to x. So that's good. So let's have a look at it. So if you've got a curve, some curve, we've been sort of talking about the instantaneous gradient at that point. Instantaneous gradient at that exact point, that's the derivative. So what we say is the instantaneous rate of change is dy dx, okay, or f dash of x. So that's the instantaneous rate of change. What's the average rate of change? So if we pick a point here and we pick a point up here, what's the average change between there and there? It's just really, if we draw a line between those two, it's just the gradient between those 2 points. In other words, yeah, you just really drawing the gradient. So what that is that that's just y2 minus y1 if we've got the coordinates of those points over x2 minus x1. That's just the gradient between those 2 points there. If you know the if that's x1 y1 and that's x2 that's x2 y2, so we can find the gradient between those 2 points, and that's the average rate of change between those points. Okay, let's have a look at a question sort of to drive this point home a little bit. So you've got an ice cube, right? And the ice cube is melting. We want to find the rate at which its volume is decreasing with respect to its width, W, when width is equal to 2 centimeters. So with any of these questions, I always encourage you to, let's just draw a cube. So we've got an ice cube. Literally, it's a cube. And so remember, a cube means that all dimensions are the same. And let's call that W because the question is using W there. And it's also got a width of 2 centimeters. Like we'll get to that back, but we're measuring these. W is measured in centimeters. That's good to know. So the first thing to do is to write, well, the question wants its volume, right? So we're talking about the volume. So let's write down the volume of this cube. The volume is equal to W cubed. Okay, nice and simple. There's the volume. And what the question wants the rate at which its volume is decreasing with respect to its width. And so what that is, that's dV over dW. Okay, the rate at which the volume is changing with respect to its width, dV dW. If it wanted the rate at which the area was changing with respect to its width, it would be dA dW. If we wanted to know what the change in time, no, not time, that's a bad example, but what's the rate of change of the area with respect to time, that would be dA dt, etc., etc. That's sort of language that you need to get used to, sort of to work with these problems. So dV dW is what we're trying to figure out. Okay, so if V is equal to W cubed, this is easy for us to figure out. Sorry, a little bit messy there. I'll just clean that up. So dV dW, the derivative of V with respect to W is that 3 comes down the front, W squared, just as if you're differentiating Y equals X cubed. Same thing, 3 comes down the front. Everything's the same, just the variables are different. So it looks a little bit strange, I know. So dV dW is equal to 3W squared. So we're almost at the answer already. dV dW, when, so that vertical line means when, W equals 2 is equal to, and I'm just going to sub in W is equal to 2. So that's 3, 2 squared. 2 squared is 4. 4 times 3 is 12. So the rate at which the volume is decreasing with respect to its width when W is equal to 2 is equal to 12. Now let's just have a quick think about this. And what are my units here? Okay, so I always need to put units in. So the volume is measured in centimeters cubed because our initial, what we're told, W is measured in centimeters. So the volume will be in centimeters cubed per, because this is a rate, And so volume, and just the tip is that whatever's on the top line will be like your first bit here, and the units of the bottom line will be what goes in here. Okay, so it's going to be 12 centimeters cubed per, and then what's the units of width? The units of width as centimeters. So it looks a bit strange, but the rate at which the volume is increasing with respect to its width is 12 centimeters cubed per centimeter. So every centimeter that the width changes, the volume is going to decrease by 12 centimeters cubed. And I hope that sort of makes sense to sort of get an idea, because you can think of it as the width is decreasing, every time that drops down 1 centimeter, the volume is going to drop down 12 centimeters cubed. Okay, so hopefully that makes sense, and hopefully you start to sort of interpret what these rates sort of mean in terms of the question. Okay, another common sort of thing that you're going to get in some of these questions, sometimes, not necessarily all the time, but are sort of things about distance, speed, and acceleration. And when I say speed, I should have said probably velocity. Speed is a little bit different. So let's have a look at a question like this. So if x is equal to 15t plus t squared, where x is the distance in meters, so the distance that, let's say, a car has traveled or something like that, how far that car has traveled, and time, t is time in seconds. Let's have a look at average velocity, instantaneous velocity, and instantaneous acceleration. Just before we do, let's just talk about a couple of these things. And so just remember that velocity is the change in distance, so change in x is our distance here, over the change in time. And so if you're asked to find the average, what that means is x2 minus x1 over t2 minus t1. Just like we talked about at the top with our average rate of change. That will be how it moves over time. And in this question, it's between 2 and 4 seconds. That would be our average, right? When we do the second one down here, this is the instantaneous velocity. So instantaneous velocity will be dx dt. Okay, so the derivative of x with respect to t, that'll get us our exact velocity. And if you also remember, or maybe you don't know, then that's okay, the acceleration of something is equal to the change in velocity over the change in time. Okay, and so if you're asked for the average rate of change, it'll be, velocity 2 minus velocity 1 over time 2 minus time 1, etc., etc. This question, though, it wants the instantaneous rate of change, and so what that's going to be is that it's just going to be dv dt, the instantaneous rate of change. I'll just leave those there to remind us as we're sort of going through the problem. Okay, so A, let's have a look at part A. Average velocity between 2 and 4 seconds. So the average, I'm just going to write down, I'll go VAV, velocity average, is equal to x, I'm just going to say x at 4 seconds minus, I'll write it just to make it really clear, x at 4 seconds minus x at 2 seconds over 4 take away 2. So there's the formula, rate of change formula, x2 minus x1 over t2 minus t1. Okay, so let's do some calculations. X of 4. So that's 15 times 4 plus 4 squared. That's my x4. I'll just put that in the brackets there. Take away, and what will it be when at 2 seconds? It'll be 15 times 2 plus 2 squared. So that will be on the top line. Bottom line is just going to be over 2 because it's changed. The time has changed by 2. Okay, and so that's equal to, what do we got? Let's just do some calculations. 15 times 4 is 60. 60 plus 4 squared is 60 plus 16. So that's 76. Take away, and then we've got 15 times 2, 30 plus 4. So that's take away 34 over 2 equals 76 take away 34 is 42 over 2 is equal to 21. So the average velocity is 21. Again, let's think about what are our units. If you think about velocity, the formula for velocity is not dx dt, right? So what's the units of x? The units of x were distance was meters per, what's the units of time on the bottom? Seconds. So the average rate of change between 2 and 4 seconds is 21 meters per second. Okay, very good. That's part A. Let's have a look at part B. Instantaneous velocity. Okay, so instantaneous velocity. So we've got x equals 15t plus t squared. And remember, instantaneous velocity is dx dt. Okay, I'm just going to save a bit of space and go to the right, sorry. Dx dt is equal to the derivative of that, so that's 15 plus 2t. There's my dx dt. Great. What we want here, it wants the instantaneous velocity at 2 seconds, and so therefore the velocity when x equals, sorry, I said x, but it should be t. I could just write it v. I'm just going to sort of show you here that this is, I didn't actually write it very well. Yeah, okay. So this here, dx dt is equal to, that's the velocity function there. I'll just to make it clear that dx dt, that's my velocity function there. Because now I'm going to use that as a function, that's why. So the velocity at 2 seconds is equal to, and we sub in t is equal to 2, so it'll be 15 plus 2 times 2. Which is 15 plus 4, which is 19. And again, 19 meters per second. And you'll see that the average rate of change between 2 and 4 seconds, average rate of change between 2 and 4 seconds is slightly different to the instantaneous rate of change when t is equal to 2. Okay, almost there. And so let's have a look at the last bit. Let's have a look at instantaneous acceleration. I'll be a bit clearer here. So the acceleration at, okay, is equal to dv on dt. We talked about that before. The acceleration is the change in velocity over time. Okay, and so we've got our velocity function here. There's that. So we just need to find the derivative of that. The derivative of 15 is 0. And the derivative of 2t is just 2. And so dv dt is equal to 2. And what you'll notice is that this does not care what the time is. It's just got a constant acceleration of 2 at all times. And so it doesn't matter whether it's 2 seconds or 3 seconds or 21 seconds. It does not matter. It's just a constant acceleration of 2. And so I'll write it, but the answer is 2. And so therefore, the acceleration at 2 seconds is equal to 2 meters per second. Hope that makes sense. That's how we sort of use acceleration, velocity, and distance to calculate various quantities. See you in the next video.